Hi everyone, we're on the sixth and final part of our intermediate physics lectures on the magnetic field, chapter 29 of your textbook. So this is something I wanted to talk about really quickly, but it's not essential, let's say, to the concepts of this chapter. It's just another application of and some more of the history of this. So the discovery and the properties of the electron. So the electron was actually discovered by a man named J.J. Thomson. He was working, I believe, at Cavendish Labs in England. Really interesting guy. So the discovery of the electron started with this apparatus that you see here at the bottom of your screen. The cathode is attached to the negative part of our high voltage producing object, and then the anode is produced to the positive side of that voltage producing whatever, our battery or power supply or whatever. The cathode then actually shoots off electrons that are attracted in this direction towards the positive anode. Now these electrons get moving so fast, and we have these screens here that allow the ones that are shooting off in a straight line to go through, and they hit this back plate here that has a phosphorescent material that's going to glow when the electrons hit it. So that was the start of the discovery of the electron. You then use this kind of thing, and instead of hitting a glowing screen, or maybe you hit a glowing screen here, is you add electric field plates and coils to produce a magnetic field that are both crossed. So again, crossed fields. This high voltage, since you have high voltage, you can turn that high voltage from potential energy. So remember our potential energy in an electric field. We can figure out, I just wrote the wrong thing, ignore that. We can figure out the potential energy of our charge in an electric field, and we turn that potential energy into kinetic energy, so we can figure out how fast it's going. And then we put it through this crossed field, and we know that in a crossed field, the thing that goes through straight has to do with the ratio of our electric and our magnetic field, right? So when we do that, we can see what is coming through in a straight line. And once we see what is coming through in a straight line from this and this, you can actually get a charge to mass ratio of the electron. So this is one way you can figure out a charge to mass ratio. And we actually have these apparatus in the department. I have my my electromagnetic 1 class use this experiment and do this experiment. And they actually vary this current, which varies the strength of the magnetic field, and they see what happens to our electrons that are deflected by that field. It's kind of an interesting experiment. And had I been in front of you guys in the classroom, I would have thought to demonstrate it for you. Okay, so another thing about the discovery and properties of the electron is this Millikan, I think I'm spelling his name right, oil drop experiment. So the oil drop experiment, an atomizer is actually just something that will create very small droplets. The most obvious example is a perfume bottle. If your grandmother had like an old perfume bottle that had one of these little bulbs on the back, they're kind of fun to play with, right? So you have this atomizer of oil, and you charge the oil, and you get the electric field adjusted just right on these two plates, that some of the droplets that fall through the center of this top plate are suspended in midair. So this telescope is actually helping you see them suspend in midair, and you can calculate from the size of the drops and all that fun stuff and the strength of the field that you are basically balancing your electric force, right? The force of these charged particles in this electric field against gravitational force. And this was the first way that the elementary charge, right? Remember, elementary charge is the smallest amount of charge we can have. This is the first way that elementary charge was measured. So that's kind of a cool historical experiment. And so is J.J. Thomson's experiments on the electron. So between those two things, that is how we got to the charge and mass of the electron as we know it today. All right, so the very final thing in this chapter, the very final concept is the Hall effect. So remember when I said that the force our charged particle feels in a magnetic field is related to the charge on the particle. So this is our magnetic force. It's related to the charge on the particle, the velocity that the particle is going, and the strength of the magnetic field. So the Hall effect takes advantage of this, and the Hall effect is basically how we can tell which charges are the moving charges in anything, right? You may have asked yourself, how do we know the electrons are the things that are moving when current is flowing through a hunk of silver, right? So this is how we know. So if we put a strong magnetic field across, so this is our direction of current, and that's actually opposite our direction of what we would call standard current or whatever. But if we put a magnetic field, which is given by these blue X's, perpendicular to the direction of current, then what's going to happen if electrons are the things moving? Electrons have a charge of -e, so -1.6, blah, 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 right? They are moving with a drift velocity, so VD, and we are crossing with this magnetic field. So as long as we're at a 90-degree angle, we can switch that to a really simple multiplication. Now, if those are the things moving, they are going to be deflected downward, right? So do your right-hand rule, right? If we had positive charge moving in this direction, and I put my hands so that my fingers bent in the direction that made sense into the page for B, my force would be upward, but oh wait, this is a negative charge, so that's going to introduce a negative sign. So this guy feels a force downward, right? So we're going to have a collection of electrons towards the bottom of this slab of material, which leaves behind excess positive charge towards the top of this material. So if we put a little voltmeter on the top and bottom here, we would measure a potential difference, right? Or in other words, we would induce an electric field between this excess positive charge and excess negative charge at the top and bottom of this conductor. So that force would also be explained by the force our little electron would feel in that electric field, right? Okay, so we reach an equilibrium that is given by that. So our Hall EMF, or our Hall voltage here on the right-hand side, for a long, thin conductor, as long as we're assuming that electric field is uniform, we just need to do this kind of math. So our Hall EMF is given by, so this is what we would measure on our voltmeter, EH times D, where D is just this distance from the top to the bottom of our conductor, right? And that is perpendicular to the direction of our current, right? It is also perpendicular to the direction of our magnetic field. Okay, so if EH could also be described by our drift velocity times our magnetic field, we could also write it this other way. So we could actually find our drift velocity by knowing the strength of our magnetic field, by knowing the thickness or the distance from the top to the bottom of our conductor, and by measuring our Hall voltage, right? So that's another way to measure drift velocity. Now, if positive charges were the things moving, again, we could figure out that positive charge is moving in a certain direction, right? So again, still current going this way. Should rewrite this top one. Let's be more clear on this top one. So this is the direction of my velocity of my electron. But remember, our traditional current is the direction that positive charge would be flowing. So it's opposite the velocity of our negative charge. Okay, so our current is still going from right to left on our page in this case. But if positive charge were the thing moving, our positive charge is moving with velocity in this direction. We take our happy little right hand, we point our fingers in the direction of velocity. We figure out that to be able to bend our fingers into the page, our thumb would be pointed down. My cartoon hands are looking awesome right now, right? And since our thumb would be pointed down, that's saying that this feels a force towards the bottom of our conductor. And if we took that same voltmeter and attached it to top and bottom, we would actually get a different reading, because here we would have positive charge collecting at the bottom and negative charge collecting at the top. So we would get an opposite reading if positive charge were really the thing moving. So this is the way you can tell which charge is moving. Now we know in our conductors, it is our electrons moving, but if you have an electrolytic solution, right, you have a solution with positive and negative ions in it, you can use this trick to figure out which charged particles are on the move, right? And so that's used in a lot of bio and chemistry applications. Okay, so our drift velocity using the Hall effect, the drift velocity is really, really small. So the Hall voltage is going to be a small thing too when we measure that. We can talk about the magnitude of the current from earlier in the chapter. We talked about the magnitude of current having to do with the charge on the particles, how many particles we had, their drift velocity, and the cross-sectional area. So there's like a cross-sectional area here that we've got material flowing through. So if you take the number of charge carriers, if you know something about the current, if you know the drift velocity from the Hall voltage, you can actually figure out that the number of charge carriers is this. So you can figure out from your magnitude of your magnetic field, your strength of your current, so your absolute value of the current, the thickness here. So in this case, thickness is over here. Your E, so here we're saying our Q is either a proton or an electron. So in this case, we're going to say electron. So 1.6 times 10 to the minus 19 is what that E is, right? 10 to the minus 19 coulombs. And that measured Hall voltage. So if you know the thickness of your strip, your current, your magnetic field, all that good stuff, you can figure out how many charge carriers. So if you've wondered before in the chapter when we've said, oh, silver has, just assume there's one electron per atom that's on the move, this is how we come up with those numbers, through experiment like this. All right, so one more application that definitely my chemists will like is a mass spectrometer. So a mass spectrometer is a way to measure masses and the abundance of isotopes. If you want a cool book, read about the uranium project in Oak Ridge and how they were separating isotopes of uranium to come up with the nuclear bombs. Really interesting stuff. This is one of the ways they attempted to do that, was putting those isotopes through magnetic fields, because there is a slight difference for ions of different masses, right? So you create some positive ions, you either hit a sample with an electron beam or X-rays, then you accelerate those ions through an electric field to get them moving. And remember, you just turn potential energy in an electric field into your kinetic energy. We'll call it 1/2 mv squared for our kinetic energy from our potential energy. And then they enter this velocity selector, right? So we have crossed fields here in this velocity selector, so we know what speed they're going. And then we enter this region right here with a magnetic field that causes our particle, our ion, to start to move in a circular fashion. So our positive ions start from rest, move through a potential difference delta V, potential energy becomes kinetic. So this happens. That's what I was writing over here. Then we go through that velocity selector. It controls the velocity of particles entering the magnetic field. They move in a semicircle with a radius that we already figured out with our circular motion example. And so we can go from that radius equation to a velocity equation. So if we know the velocity, we know there's a radius that it's going to hit. Since we're going to move in a semicircle, we're going to strike the detector 2r away from where we started. So there's a center of our circle here, and we've got our radius of motion, right, in either direction, if we're going in circular motion in this magnetic field. And since we're hitting that detector, you're going to see slight mass differences that are going to be measured. So here's the equation you would use. We've got kinetic energy of 1/2 mv squared. We can describe our V in terms of our charge. So if we've just ionized it once, we have like 1 extra proton, right? So we have a charge of 1.6 times 10 to the 19 minus 19 coulombs. We know what magnetic field we've put it in. And we're going to see a difference in mass from a difference in where it hits the detector, right? So if I do all this math, I'm going to see this kind of result, right? So a slight difference in mass, it's a different isotope because it has an extra neutron, is going to be given by hitting the plate at a slightly different spot. All right, a cyclotron is another application. These are used to accelerate particles to a large kinetic energy. They're used in things like the Large Hadron Collider. They're used to study atomic nuclei. So there are some of these all over the country in some of the national labs. They're really cool. You can even hit like biological proteins with them to study what's going on with the structure of those proteins. All kinds of cool stuff. You can also produce radioactive materials. So if you know somebody who's had radiation treatment, this is one way you can produce radioactive materials for that radiation treatment. So the particle is accelerated across this gap. There's an electric field across that gap that accelerates the particle. And it enters these things called Ds, literally because they look like a capital letter D. So when they enter those Ds, they go through the magnetic field in this semicircle, right? And your maximum radius of your Ds gives the max velocity that you can get to. So they jump to larger and larger Ds as you get them moving faster and faster, right? So again, your kinetic energy of your particle can be figured out using that velocity I've got right there. 1/2 mv squared, your kinetic energy is given by this equation over here for a cyclotron. Okay, so I'm just going to end up this chapter with a summary of the right-hand rules. Remember, there are 3 different ones, even though they're all very similar, that we used. The first one that we used, we want to make sure we're using it in the right place. So we've got a magnetic field that's being produced by a current. So this is the field produced by the current, not an external field. So the field produced by the current, we stick our thumb in the direction of the current, and our fingers of our right hand are going to curl around in the direction of the magnetic field. So we get those loops of magnetic field around a current of wire in that way. And that wire could be going straight, or it could be a loop of wire, and that just tells us how the field lines kind of loop inside and outside the loop. All right, so here's a description of what you do that I just gave you my own version of. Our second situation is the force on a current due to an external magnetic field. So I'm going to throw in an extra word there. So this isn't the field that this current is creating. This is an external field, a field created by something else that this current is in. So for this case, I times the length of the wire that's in the field crossed with B. So we're going to put our fingers in the directions of our current. We're going to rotate it around so our fingers naturally bend in the direction of B. So that's I cross B, and the resultant vector that's perpendicular to them both is given by our thumb. So whichever way our thumb points. Now, if we're talking positive current, the force is the way our thumb points. Okay, and then the third one, the force on an electric charge, I'm going to be specific and say positive Q. And again, I'm going to throw in the word external, even though a single charge is not really going to produce a steady field, right? Okay, so again, the force is Q times V crossed with B. So since V is the first thing, we're going to point our fingers in the direction of V. We're going to rotate our wrist around so that our fingers naturally bend in the direction of B. And that means our thumb is pointed in the direction of F if Q is positive. So if Q is negative, we just give ourselves a negative sign and go in exactly the opposite direction as our thumb is pointed. Okay, I hope that helps you guys with your homework. We'll start on chapter 30 next time.